So, a series of questions associated with molecular structure, vast range of concepts here, but a much smaller range of types of questions that they will ask. I'm going to go through this probably relatively swiftly because in many cases you either know it or you don't. And one of the first types of things that you know or you don't are how to draw simple, what I call Lewis dot structures, what you call dot and cross diagrams, giving you nice simple molecular structures or structures of species, I should say. Select all the molecules from the list below that have bond angles of less than 109 degrees. And we start off not with the molecule, but with a cation. So anyway, NH4 plus, only way you can draw it, nitrogen in the middle, 4 hydrogens going around it. No lone pairs or anything like that, because however you think about it, the nitrogen starts with 5 valence electrons, uses 4 in the bonds, and then of course there's that plus to take care of the 5th one. 4 groups of electrons around a central atom create a tetrahedron, because in this case all 4 of those groups of electrons are bonding groups. That means that these are all identical to each other. 109.5 degrees is the angle. BF3, one of those I wish they wouldn't put on the A-level because they don't really discuss it correctly. But anyway, the boron bonded to 3 fluorines. Boron starts with 3 valence electrons, uses up all 3 of those, so there's no silly lone pairs or anything on the boron. So an atom with 3 groups around it, trigonal planar. And because each of these groups are bonding groups, it's going to be a perfect one of 120 degrees. NH3, which like NH4 plus, both appear to be nice common questions on the exams. NH3 just like NH4 plus, except you've lost one of the H hydrogens there, the H plus, replaced it with a lone pair. So 1, 2, 3, 4 groups means it's tetrahedral, but when only 3 of those groups are bonding groups, it is instead called trigonal pyramidal. Starts off at 109.5 degrees, but this lone pair is more repulsive than bonding groups. The lone pairs always squeeze the bonds together, in this case making it about 107 degrees, but less than 109.5 is what we're interested in. CH4, like NH4 plus, perfect tetrahedron with 109.5. And finally SF4, again, not quite sure why this is on the syllabus because it just kind of pops in without any real context for it or further discussion that would be appropriate, but sulfur surrounded by the 6 fluorines makes a perfect octahedron in which the angles are 90 degrees. So those that are less than 109.5, the trigonal pyramidal at about 107 and the octahedron at 90, C and E. Said ammonium was a popular choice of the examiners. So the year after this, in 2015, they asked about the bond angle in the ammonium ion. There it is. Why is this the case? Because groups or pairs of electrons move towards positions of minimum repulsion or of maximum separation. And when you have 4 of these, the best way for them to arrange themselves is this tetrahedron. So question 38, part of a bigger question that I'll finish off later on in this set of videos around study properties of silicon, blah, 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 structure similar to that of diamonds. So that's what it is there. SiSi bond angle 109.5. More importantly, each silicon atom bonded to 4 other silicon atoms. So if we think about this one here, 1, 2, 3, 4, and so on. Name the shape that has this bond angle. Well, we just talked about it quite extensively. Tetrahedron with those angles of 109.5. Hydrofluoric acid will dissolve silica, blah, 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 contains the SiF62- ion. Use the information from the table below to draw the shape of this, showing the angle, give a reason for your answer. Well, they tell us there are 6 bonding pairs and no lone pairs. So if we think about the silicon, it is just going to have 6 fluorines around it like this. The angles will be 90 degrees. It's an octahedron. And the reason why 6 groups of octahedral geometry is so they get as far apart as possible from each other. And the only best way to get 6 groups as far apart as possible from each other around a central atom is this nice little octahedron. You can think of it as the set of 3-dimensional axes if you want. That's the x-axis, the y-axis, and the z-axis. However you want to think about it, octahedron with a 90-degree angle. So a couple of very similar questions associated with ammonium. and ammonia are. So first of all, we've got ammonium ions are tetrahedral, and then we're going to talk about ammonia are. So much as in previous questions, talking about ammonia are to start with. Nitrogen in the middle, 3 hydrogens, because nitrogen starts with 5 valence electrons. It's used up 3, must have 2 left, giving it therefore that lone pair. Using my common sense, no reason not to have the nitrogen with the 3 bonds and the lone pair. 4 groups of electrons would make this central atom tetrahedral. However, in this particular case, one of those tetrahedral branches that would be at 109.5 from each other is occupied by a lone pair of electrons. Lone pair of electrons more repulsive, so therefore push these together, so the angle is less than 109.5, or as we said before, about 107. Dot and cross diagram for ammonium. Nitrogen in the middle. You pick it however you want it. Let's say it has the 4 X's, and then each hydrogen comes in with the dots. I really do object to this so strongly, but never mind. That's what it says, draw a dot and cross diagram. I would personally prefer that you either just draw the bonds, as we did previously, or just have a pair of dots to represent the shared electrons. But anyway, that's the university perspective versus the A-level perspective. Hydrogen can form a range of covalent hydrides such as water and beryllium hydride. The student said since you've got 2 hydrogens to the other element, same in both compounds, the shapes will be the same. Is this student correct? Well, H2O, you've got the oxygen that starts with 6 valence electrons, uses 2 up to bond to the hydrogens, leaving 4 behind, so 2 lone pairs. BeH2, beryllium, which of course they should really emphasize the fact that beryllium is being weird here, right? It's an alkaline earth metal, but it's making covalent bonds. And that's something that's so important that beryllium, while it's a metal, is very definitely a metal. It does like covalent bonds rather than ionic bonds because it's not as electronegative as other metals are. But anyway, that was too much. For this particular question, beryllium's got 2 valence electrons, uses both of those to make these bonds to the hydrides, so has no lone pairs left. Water, therefore, 4 groups of electrons around the oxygen. It's based on a tetrahedron, beryllium hydride, only 2 groups of electrons around the beryllium, thus it is based on a linear geometry. H2O will be bent because 2 of those parts of the tetrahedron are lone pairs, thus making it bent. Beryllium hydride, no lone pairs, very distinctly linear. Student is not correct. Name the shape of the ClF6 plus ion. Not overly sure how students are supposed to answer this the way that I've seen them being taught. But anyway, you're going to have a chlorine in the middle of the 6 fluorines. Chlorine starts with 7 valence electrons, uses up 6 of those to make the bonds to the fluorines, but then it's plus, so the 7th one goes away. So 6 groups of electrons around the chlorine, adopt octahedral geometry, so they're as far apart as possible. ClF2 plus, ClF2 minus, 2 other ions containing chlorine atom. Students say their shapes must be different. Is the student correct? Justify your answer using VSEPR. Question in my mind was how far to take this. But anyway, ClF2, you've got 2 bonds to chlorine, so there are 5 electrons left. However, you've got a plus sign, so there's 4 electrons left. Thus, there are going to be 2 lone pairs. So ClF2, the chlorine is going to have 2 bonds to the fluorine, 2 lone pairs. It will be bent, just like water, just like several other ones that you've seen, the 2 bonding and 2 lone pairs. ClF2 minus, again, 2 bonds to the chlorine, so 5 electrons left of the 7 with which chlorine starts, but the whole thing's negative, so you've got to give it another electron, so there's 6 electrons left. So therefore ClF2 has got 2 bonds to chlorine and 3 lone pairs. Okay. Now the actual structure of this is a linear one, but you're not supposed to know that at your level. But what you are supposed to note is when you've got 2 bonds, 2 bonds, 2 lone pairs, 3 lone pairs, they've got to have different structures. Question 44, one of the more inane types of A-level question because you discussed this at GCSE. But anyway, forming calcium chloride from atoms of chlorine and calcium. Calcium has 2 valence electrons, and so we write it with 2 crosses. Chlorines each have 7 valence electrons, so we write those as 7 dots. So when calcium, which wants to make calcium 2+, is approached by chlorines, which want to make Cl-, the calcium gives up its 2 electrons, 1 each to each of the chlorines, thus making Ca2+ and 2 chlorides. Meaning of the term electronegativity, ability to attract electrons in a covalent bond, the shared electron pair, and explain why this increases across a period in the periodic table. Very unsatisfactory explanation at A-level. But anyway, what you do is you say it's the valence electrons that are involved in making bonds are in the same shell across a period. However, as you go across a period, the nuclear charge increases. Thus, the electrons are going to be attracted to the nucleus that has the higher nuclear charge, in other words, the nucleus of the atom that is further right. So the further right you go, you get that increase in nuclear charge, so an increased attraction to the valence electrons in the shared electron pair. Table below gives electronegativity values, some elements, actually of some atoms, not of elements, but never mind. Use the data in the table to identify any dipoles present in the following bonds and make their polarity clearly. So N and H, there's H, there's N. We have differences in electronegativity, 2.1 and 3.0. The 3.0 for the nitrogen, higher than the 2.1 for the hydrogen. Thus the nitrogen will be slightly negative and the hydrogen slightly positive. Same idea for oxygen and chlorine. Oxygen 3.5, chlorine 3. 3.5 is bigger than 3, so the oxygen will be slightly negative. Chlorine will be slightly positive. Use the data to give a reason why aluminium chloride, considered to be covalent, aluminium oxide, is ionic. Well, looking at the data, there's AlCl. You've got the aluminum is 1.6, the Cl is 3, so the difference in electronegativity is 1.4. That would be usually considered to be polar covalent. Okay, when the electronegativity difference is 0 or close to 0, it's a non-polar covalent, up to, depending upon who you speak to, somewhere 1.82, something like that, then it would be polar covalent, at which stage it would cross over to ionic. As we see with the aluminium oxygen, because here you've got oxygen 3.5 minus the 1.6, difference of 1.9. Bigger, and so one would define that as being ionic. Actually, of course, even this in ALO, more people would consider the bonds to be covalent, just a nice polar covalent, it making one of those nice big infinite covalent structures. But anyway, at the A level, AlCl 1.4, that's a little bit too small to be called ionic. ALO 1.9, that would be one just about big enough to be called ionic. Carbon monoxide, 2 covalent bonds, 1 coordinate bond. What's meant by the terms covalent coordinate bond, indicating the difference between them. Both of them involve 2 atoms sharing 2 electrons. Covalent bond, each atom puts in 1 electron into that pair of electrons. Coordinate bond, both of the electrons in the bond come from 1 atom. And so using either color or crosses and dots or both, you can illustrate the covalent. There's X puts an electron in, Y puts an electron in. Coordinate, still bonded X and Y, but here Y has put in both electrons. One example species, well, all coordination compounds you can think of as being coordinate bonds in which the metal cation is in the middle and the ligands are donating a pair of electrons into the bond. One of the other classics is aluminum chloride. You got AlCl3 there, AlCl3 here, but instead of it being a monomer in which the aluminium only has 6 electrons around it, it dimerizes so that you have the chlorine from one of the AlCl3 units forms a coordinate bond to the aluminium of the other AlCl3 unit. A poor naive GCSE student said apart from metallic bonding, bonds are either ionic or covalent. An A-level student said not really true, bonds could be intermediate between ionic and covalent. State one factor that governs what type of bonds elements form, again should be atoms, and explain how this leads to different types of bonding. And the big thing is the electronegativity of atoms, and particularly the electronegativity difference between two atoms that are going to bond. If the difference in electronegativity is 0, it's a nonpolar covalent bond. Somewhere between 0.2-ish, and in that range 1.6 to 2, we'll say it's a polar covalent bond. And anything bigger than whatever you happen personally to define as the cutoff is going to be ionic. Describe the electron density in each type of bond: ionic, covalent, and intermediate. Well, perfect covalent bond is perfect sharing. So here is a perfectly symmetrical electron cloud being shared by X and Y. Intermediate, Y starts to suck the electrons a bit more, so it is an asymmetric cloud. And ionic, Y has completely sucked all the electrons to itself, so X would be the cation, Y would be the anion here. So two elements from this list produce the most ionic bond. Well, looking at where they are on the periodic table, you want the most ionic bond is the one where the atoms have the highest difference in electronegativity. If we look at the metals, sodium is less electronegative than magnesium, so it will make more ionic bonds. And then the non-metals, oxygen more electronegative than bromine, so it will make the more ionic bonds. So sodium and oxygen together. Now the dot and cross diagram for N2H4, so I'm going to draw it properly to start with. Nitrogen wants 3 bonds, hydrogen wants 1 each, so that means the nitrogens have to be bonded with each other, and that uses up one of the desired bonds for each one, leaving 2 more bonds, which are filled on each nitrogen by 2 hydrogens. Anytime nitrogen wants 3 bonds, it has a lone pair left. Now drawing it in terms of dot and crosses, there we go. So we'll give hydrogens dots, nitrogens crosses, and of course because different nitrogen atoms have different colored electrons, we'll illustrate that too with that. This really is the better way to think about it. It gives you so much more clear to see information. What's a polar covalent bond? Well, a covalent bond is where you're sharing electrons. And when those electrons are not equally shared, it becomes polar. And the reason, of course, they're not equally shared is if the atoms have a difference in electronegativity. Very similar molecule to the last one, hydrogen peroxide, H2O2. Oxygen wants 2 bonds, hydrogen wants 1. So again, the 2 oxygens have to be bonded, using up one of those bonds they each want, leaving 1 bond for each oxygen to go to the hydrogens. Anytime oxygen makes 2 bonds, it's got 2 lone pairs. And there is, without further comment, the dot and cross diagram. 5-amino-2-hydroxybenzoic acid can be used in medicine to treat a number of conditions. This is believed to work by removing free radicals. One of these radicals is the hydroxyl radical. This can be produced by the homolytic bond fission of hydrogen peroxide where the OO bond is broken. Draw a dot and cross diagram of the hydroxyl radical. Well, there is, fortuitously, our beautiful Lewis dot structure of the H2O2, and we're breaking that bond there. Now it's homolytically being broken, which means that 1 electron goes to each oxygen of the 2 electrons in this bond. So there's one of the radicals that we get from it. There's the dot and cross to show you, breaking the bond again there, and there we have the same thing, showing you the oxygen has got 1 unpaired electron there, oxygen with 1 paired electron that came from the homolytic bond fission.